Miss Cantwell. I am so glad to be able to record this video for you guys to kind of help you look at the main ideas of the content a little bit. I hope you guys are staying safe and happy and entertained, and that you are doing well. If not, for whatever reason, just let me know and I'll do what I can to help. You can always reach me Google Classroom or through email, okay? So the first thing that I want to do today is I want to look at some basic information that you may have missed from previous lessons, or just that we haven't coincided, or we haven't really had a chance to go over. So waves. The whole thing with waves is that it's a repeated motion, and that it's a means to transport energy, not matter, but energy. So there's a couple different ways we can classify them. We can classify them by kind of the shape, or what they look like. So we have transverse waves. Those go up and down like you see. And we also have longitudinal waves. Those look kind of like a slinky. So the main thing, we can also classify them as either mechanical. Whoops, that doesn't go there. We can classify them as mechanical. I'm going to do those in a different color. Or electromagnetic. Okay, so in transverse waves, the particles vibrate up and down, and the wave energy is transmitted forward. In a longitudinal wave, the particles vibrate side to side, and the wave energy is transmitted forward. So those are not, I said shape, those are not shape, those are the direction of energy transfer. And then mechanical waves need a medium. That means they can't travel through the vacuum of space. They have to have something to bounce off of. Electromagnetic waves actually travel fastest without a medium, but they can go through different mediums. So EM waves don't need a medium. Okay? So then what we typically do when we talk about waves is we look at light waves and sound waves. Okay? So light waves are transverse. Remember, that means the particles go up and down, and the energy gets propagated forward. And they are also mechanical waves. Sorry. They're not mechanical. They're electromagnetic. That means they don't need a medium, and in fact they travel fastest without a medium. Sound waves, on the other hand, are longitudinal. Okay, that means that the particles go side to side and the energy propagates forward. And these are the mechanical waves. That means they have to go through a medium. Okay? We've also talked about some different wave parts. Okay, so I'm just going to draw a transverse wave for you now. There's a dotted line that we draw. That would be the equilibrium line. That's where the particles would be if there was no energy moving through there. So this is what we call rest. This is their resting position. We have also amplitude, which can be above or below rest. That tells you how far away from rest that the particle is moving. Okay. We also have wavelength, and the symbol for that is lambda. that goes between two identical wave parts. Okay? So we need to know amplitude to talk today. We need to know wavelength to talk today. And then we also need to know frequency. Frequency is how often the wave occurs. So how many pulses per second? Okay, how many pulses per second? So those are the things that we need to talk about today. Now let's look at a presentation that we can talk about. So the first thing we're going to do is we're going to look at sound waves and some of the properties of sound waves. Remember, sound waves are longitudinal mechanical waves. That means they require a medium to go through. So intensity is one of the properties of a sound wave that we look at. And intensity is a measure of energy flowing through the wave at a time. So how much energy flows through an area over time, and this is what's measured in decibels. So if you hear about airplane noise or headphones that are rated for a certain number of decibels, that's what it's talking about, how intense that sound is. And intensity is an actual measurement of energy, which is proportional to the amplitude of that wave, so how far the particles are being displaced from rest position. If you have a higher amplitude, you have a higher intensity. Okay? So intensity is energy and amplitude. All right? Loudness. Loudness, on the other hand, is our perception of intensity. It's a perception, so how we perceive that intensity. And that's going to be different from person to person. You guys know, I have said in class before, I can hear your music from your earbuds. You're going to hurt your ears. And then a student, Jalen, typically will say, it's not hurting my ears, it's not that loud for me. My daughter does the same thing with her headphones. Things are turned at a very, very high volume. And to me, it's too loud. But it's relative between us based on a couple of things, age and then just personal perception. It's subjective. So volume or loudness is not something that we really can say absolute with a specific sound wave. And we can also say that it's affected by the pitch of the sound. Okay, so you guys know, and you guys, younger people, are actually able to hear very, very high-pitched sounds. And older people start to lose that high-pitched hearing. It also depends, typically, they've done some studies that show that males actually hear better when the pitch is lower, when it's a lower sound, and females hear better when the pitch is higher, when it's higher up. And that's because that's what our bodies are used to, because that's our natural frequencies or our natural pitches that our vocal cords make. There's a lot of different ways that you can talk about that, but that's just a little bit. Okay, so the next one is frequency, and we defined frequency before when I was writing on the screen. Frequency is the number of oscillations. Oscillations just means it goes somewhere and then it comes back to the same spot. So the particle goes out here and then it comes back to the same spot. So that's one oscillation. You can also call it a cycle or a pulse. So imagine like a water drop. Okay, every time that water drops would be a cycle. And it's measured in hertz. You guys have heard that term before. Hertz is just 1/seconds. It's an inverse second. Sound waves have frequencies, so a measure of how often they're vibrating per second. And then the way we perceive that is called pitch. Okay, so you may have like a note on an instrument that is a certain frequency, and then we would assign that note a letter, A, B, C. That would be the pitch we assign to it. The difference is frequency is an absolute direct measurement that we can take, and pitch is kind of, it's a little bit subjective. We, as humans, are not going to be able to interpret a difference between 2 or 3 hertz, but an oscilloscope or something that measures frequency directly will be able to distinguish that. Okay, so again, this is where if we have a high frequency, then we will have a higher pitched note. So if things vibrate more frequently, then they will create a higher pitched sound. And remember that that pitch also plays a role in intensity, because sometimes the higher pitched sounds are more painful for us. Like you use a dog whistle to control dog behavior. They're so high pitched that we can't hear them, but it's in a hearing range that is actually slightly painful to the dog. Alright, so now we're going to look at electromagnetic waves. And electromagnetic waves are special waves that are formed when we have an electric and a magnetic field that kind of oscillate perpendicular to each other. Okay, so that's all a lot of words that you don't need to know. What you do need to know is that they do not require a medium. That's super important. We don't need a medium here. Do not need a medium. And their speed is affected by the medium they're traveling in. So they're going to go fastest when there's actually no matter around them. They're going to go fastest when they are in a vacuum. Fastest when they're in the least dense medium. And remember, density is just like how closely packed the particles are together. So electromagnetic waves would travel faster in a medium like this on the right, where there are fewer particles spaced out. And then they would travel more slowly in a more dense medium. So they slow down when they have stuff they run into. Okay. In a vacuum, which means there's no matter, it's not a Dyson, okay, it means there's no matter, they all travel at the speed of light, which is 3 times 10 to the 8th meters per second. So really that's 1, 2, 3, 4, 5, 6, 7, 8 meters per second. Okay, that's real fast, and we cannot approach that speed. There is a formula that we can use. We will not ask you to do math, but it's important for you to look at the relationship. So you'll notice that velocity is on the y, and it depends on the frequency, how many oscillations per second, and the wavelength, how long the wave is, how long a cycle is. So it's directly related to both of those things. Okay. The speed of the wave only changes if the medium changes. Okay. If the frequency is higher, the speed will stay the same. The only thing that affects the velocity is the medium. So it only depends on the medium. It is a product of the frequency times the wavelength, but it only depends on the medium. So that means we're only going to change the speed if we change the medium. If we have a higher frequency wave, the speed is going to be the same. That means the wavelength will have to be smaller. If we have a lower frequency wave, the velocity will stay the same in the same medium, and the wavelength will have to be bigger. Okay, so frequency and wavelength are inversely proportional here. If one goes up, the other one has to go down. And this is how we organize the electromagnetic spectrum, which you may have heard about in chemistry. Okay? Now, if we change media, this is important. So if the medium is the same, then we'll have the same speed. For light, if we go into a new medium, so we change the media, then we're going to change the speed. And then for light, that means if we increase the density, the frequency will stay the same, but the velocity and the wavelength will decrease. Okay, then if we decrease the density, the frequency will still stay the same because changing the frequency changes the wave, and that's not what we're trying to accomplish. If we decrease the density, we will increase the wave speed, and we will also increase the wavelength. Okay? The frequency does not change when the medium changes, but speed and wavelength do change. Okay, so again, we talked about the electromagnetic spectrum before. You've seen it in chemistry. It's organized based on wavelength and energy. So if you look at it, let's do this color. So down here you have radio, micro, and infrared rays. These down here are primarily used for communication. Oh, I forgot this guy. And are not very strong. They have a low energy, they have a low frequency, and they have a big wavelength. Infrared gets a little bit more intense. Then you have the visible spectrum, which is a very, very narrow range. And then above that you have ultraviolet, X-ray, gamma rays. These are going to have the most energy, they have the highest frequency, and they have the lowest wavelength. Okay, so the key things to remember is that wavelength and frequency are inversely related. Frequency is proportional to energy. Okay, and then here at the left end, we will have high wavelength, low frequency, and low energy. And then again at the right, we will have high frequency, high energy, and low wavelength. Okay. So now we're going to talk about, this is the last piece. So we're going to talk about two different wave behaviors that happen in light waves and sound waves. But we're going to talk about them as they apply to light. So these are the behaviors that are responsible for you being able to see yourself in the mirror, or you being able to look at an image through water and it being distorted from reality. So reflection happens when a wave hits a boundary and bounces off. So we have the law of reflection, which says that the angle of incidence, which is the angle that the ray approaches the mirror, so that's the angle of incidence, that's going to be equal to the angle of reflection, which is the angle that the ray of light leaves the mirror. And these angles are measured from a line. It's called a normal line. So that normal is an imaginary line that is perpendicular to the surface. So notice we're not talking about the angle between the ray and the surface. We're talking about the angle between the ray and the imaginary normal line. Okay, so this is telling you again what I just said. The angle of incidence is going to be equal to the angle of reflection. So that's how we see images. Those angles are equal. Refraction happens when we change media. Okay, so when we change media, like if we go, this being a light wave, if we go from a vacuum or space, and then we go into any other kind of medium, we are going to change the speed of that wave. That's what we just talked about. So the angle of incidence will not equal that angle of refraction, okay? So normally, if the speed of the wave had not changed, okay, if the speed of the wave had not changed, this ray would continue going at the same angle, okay? But because we've changed speed, we're actually causing the light to bend, and that's creating that refracted ray, okay? So again, refraction is when we are changing speed. If it had reflected, it would have just bounced off at that same angle. The amount, how far it bends or how much it changes its speed is controlled by an index of refraction. So it's a ratio of from one surface to another, and we can find there's calculations you can do, but we don't do that at this level. And then also each material is going to have its own index of refraction, and it's compared to empty space. Okay, so here's a chart that's showing you indices of refraction for different materials. So in a vacuum, the index of refraction is 1. Okay, so if we go from a vacuum to a vacuum, we will not refract. If we go from a vacuum to air, okay, then it will bend a little bit. And you can see that these are in increasing order. The highest one would be silicon. Okay, silicon has the highest angle of refraction, which means that the wave would bend more. Okay. So if we're looking at these two, so if we're coming from a vacuum and we're going into diamond, okay, and then we're coming from a vacuum and going into water, the ray going through the diamond would bend more than the ray going through the water, because diamond has an index of refraction of 2.41 and water has an index of refraction of 1.33. The last thing that we have to talk about is that when we change speed, there's kind of a convention. So again, if we were to look at this purple line here, or I guess it's not purple. It looked purple to me at first. So if there was no refraction, it would continue on this way. Okay, so this one's saying the density of medium 1 is less than the density of medium 2. Okay, so this one has a higher density. We already know that that means it's going to slow down. Okay, so it was going at a speed in medium 1 where it's less dense. It's increasing its density, so it's going to slow down. So when it slows down, we say that it bends towards the normal. Okay, so this means that the angle of refraction is going to be less than the angle of incidence. Okay, you will not need to know that. What you will need to know that if it's slowing down, it bends towards normal. Okay, remember the normal is just that imaginary line that's perpendicular to that surface or the boundary between media. If, on the other hand, we go to a less dense medium, so that means medium 1 has a high density and medium 2 has a low density, we know that that wave is going to speed up. So again, we would continue normally like this. The yellow line represents a continuation. It's not straight because I'm not a robot, but I did my best, okay? This refracted ray is going to bend away from the normal, okay? So that means the angle of refraction is going to be much greater than the angle of incidence. Main thing you need to know is that it's going to speed up, and that means it's bending away from normal. And this happens when we go from a low density to a high density for light. Okay? And that is actually it as far as the slides for today. But again, I just want to let you know, I know it's frustrating because you couldn't ask me questions while I was in the middle of that whole spiel. But I want you to know that you can always email me. You can always message me on Google Classroom if you have any questions at all. And we'll work together. We'll figure it out. There's also office hours for me on Thursday at 1 o'clock if you would like to join that and ask questions as well. If you are working only through the packet, you might have some different questions, and that's okay. You need to, you can just email me, you can come to office hours, you can do what you need to do. If you're working through Edgenuity, just remember that the materials and the activities in Edgenuity, those aren't being graded. What's being graded is the response to your Google form quiz, okay? Which you have as many attempts at as you need to get the grade that you want, okay? Again, I really hope you guys are doing okay. I miss all of you, and I can't wait to see you again, however that happens. Please stay safe, take care of each other, take care of yourselves and your families, and just get a hold of me if you need anything, okay? I miss you guys. Bye.